Welcome to this week's webinar. And in this webinar, we're going to do a deep dive into Visual Intro to Python Unit 1. And in this course, you learn Python coding by drawing. I'm Sheila Crawford Bunch. I'm the Director of Education for NCLab. And this webinar series is made possible by a Nevada State Library Archives and Public Records Continuing Education grant funded by the Institute for Museum and Library Services through the Library Services and Technology Act. NCLab is a self-contained desktop platform where you can learn and use computer programming, modeling, and many other STEM skills. And STEM, of course, stands for science, technology, engineering, and math. And today it's really STEAM. We're going to stick an A in there for art. You learn through self-paced, self-graded courses. And today we're going to look at the first unit of Visual Intro to Python. Then apply the skills using the apps in Creative Suite, and the app that we use is the Python Turtle. And we're going to connect coding to art, math, design, and robotics. So I think this is important that when people are learning skills, that it's not in a vacuum. They're going to eventually use these skills applied to some area and get inspiration from these areas as well. We're going to learn about the Python Turtle itself, and I'm going to review some math, some basic math on the XY coordinate plane. One of the problems we've seen is that people are either rusty with this information or they're just learning it if they're kids. And so I've included quite a bit of basic information on the XY coordinate plane. And then we'll go through the course. We're going to learn how to practice the concepts in Unit 1 and create some projects based on the unit. And I'll try and tie concepts to math, art, design, and robotics as we go. So a little more formally, with the Visual Intro to Python course and the Python Turtle app, we're going to write simple programs in Python, learn how to draw lines, arcs, and figures in the XY coordinate plane, use indexed for loops and nested loops to draw polygons, and it's not just polygons, there's other repeated patterns. We'll create games and designs based on Python Turtle programs and research how drawing relates to mathematics, art, design, and robotics. Just a note at the bottom, we used to call this course Python 1. It's now called Visual Intro to Python. And one of the things we did when we changed the name is we reorganized the course. So I'll show you shortly how it's organized now. In terms of prerequisites, really, it's a good course for users who are ready to type coding scripts and have just a basic understanding of the XY coordinate plane. Younger children can experiment with some pre-made programs in the Python Turtle app to see how changing the values can affect the outcome, and I'll show you that. As long as they have some typing skills, you know, I've had people just dive right into the Turtle course or Visual Intro to Python rather than going through Carol. They learn a lot of the same skills. Carol appeals to some people, and this course appeals to others. Educational standards, of course, libraries often work with schools and provide a lot of practice time that schools simply don't have time for. And of course, a library can be within a school as well. The computer standards that are generally in use these days are derived from the CSTA and ISTE standards. There's some combination of them. In terms of how it relates to mathematics, Visual Intro to Python is a great companion curriculum for middle school or early high school because they're really trying out their skills in these coordinate planes and working with number systems and functions and geometry, and it's a great way to practice these skills. I pulled two standards from CSTA. Really, the skills we're learning are firmly entrenched in algorithms and programming. And now CSTA expects that children in grades 3 to 5 will create sequences, events, loops, and conditionals. But anyone starting in programming is going to have to learn that. And so our Unit 1 really works with sequences and loops. And then you start thinking about loops more as control structures. And in Unit 1, Section 5, we get into nested loops. So that's a slightly more complex version of a loop. And of course, you're using a real programming language. You're using Python rather than pseudocode to create these. So you're learning language skills. For ISTE, really what we're doing is developing computational thinking. They're formulating problem definitions. They're using technology. They're abstracting models and building their algorithmic thinking. An algorithm is just simply a method that you use to solve a problem. You can write out the steps and you can program them into a computer. We're also digging a little bit into math standards, and there's several that could apply. One that stood out to me was this business of drawing polygons in the coordinate plane given coordinates as vertices. This is something that matches fairly well to what you can do in this Unit 1 part of the course. And the math practice standard that applies, the most applies is MP8, which is to look for and express regularity in repeated reasoning. And of course, that is talking about the for loops and the nested for loops. A little background on the Python turtle. It was originally designed at MIT by a wonderful team there back in the mid-60s that was looking for a way to teach children how to program. We're still doing the same thing now. So they developed a language called Logo, which is Greek for thought. And then they also built this turtle. And it was some junk that they put together with wheels, and it was trailing a pin behind it. So that's where the drawing component came in. It was drawing lines on the floor based on code. It was hardwired to the computer. So a little primitive, but our turtle is basically a modern version of that old turtle. And why turtles? Well, in the 1940s and 50s, W. Gray Walter was developing robotics based on animal behavior. It was partly to understand how our brain works, but of course that translated into building robotics as well. And one of his tortoise robots, is at the Smithsonian. So that's pretty cool. This is the turtle has got some great history to it. And the other part of drawing, of course, is very playful. So you can learn some pretty advanced skills by drawing. And MIT, they were great believers in constructionist learnings. So once someone learns a few skills in the course, they really should go to the app and play with it, draw stuff. They may want to read up on these people who worked at MIT in the 60s. It's a nice piece of history. Seymour Papert is one of the great movers and shakers of the 20th century. So why are we learning Python? We're not learning Logo, and there have been, the turtles have been used in many languages. But Python is a widely used language these days, not just as a teaching language, but it's used in practice. It's what you call a general utility language. It can be used to perform complex computations and manage file systems and analyze data. It's very fast. And so it's used for a lot of back-end operations. And this is code that performs tasks behind the scenes. So you're not going to see Python in your face is working in the background or in the back end. It's a very well-documented language, and it has a lot of libraries. We looked at some of those libraries when we were playing with encryption. And it has a whole library on turtles. So I put a link in there to the documentation on the python.org site. I do want to mention that some of our turtle characteristics in NCLab are not the same as the one in Python. For example, the color commands that we use their keywords are capitalized, and they're compatible with Plasm, which is the language used in the 3D modeling app and course. And we also have thrown in a few other commands such as Go. And the reason why Go is a command is because many students have learned Carol, and so this was a way for them to segue from Carol to Python. So we've included Go. The official word for go, or drawing a line, moving the turtle forward, is FD for forward. It's not that critical because the turtle's primarily a teaching tool. When you're running graphics in real life, you're more likely to use Matplotlib or one of the other libraries. But it's nice to know that there's an extensive turtle library on the Python website. And here, I'll just show it to you real quick. Why not? Let's go take a peek. Okay, so you can see there's lots and lots of commands. And some of these will work in NCLab. If they don't work, they don't. The one that I've noticed in particular is the color command. But if you have just an open IDE environment, these will all work. So interested in playing with turtle graphics, there it is. One of the reasons why some of these commands don't work on our platform is that we're talking back and forth to a server, so sometimes we have to customize commands to make that work as an educational tool. All right, so let's get into a little bit of basic math, and these slides will be helpful when someone doesn't understand the coordinate plane. So really starting from the basics, the plane is formed by an x-axis that runs horizontally and a y-axis that runs vertically. These are perpendicular. And then you form a grid by making equally spaced parallel lines. The grid interval, and in our case, our grid interval, the default is 10. So each of these spaces is worth 10. But grid intervals, of course, can change depending on what you're trying to do. It does extend infinitely in the x and y directions, so that forms an infinite two-dimensional plane. In real life, of course, we restrict the limits, or we might have trouble running our calculations. The way the coordinate plane is numbered is that the point of intersection between the x and y axis is called the origin, and that is 0, x and 0, y. And we write it like this. In parentheses, we have 0, 0, and the first 0 stands for the x value, and the second is the y value. And from there, if we go to the right, the numbers are positive integers. Well, they can be real numbers as well, but we're spacing them on integers. And to the left, the numbers are increasingly negative. Same thing with y. If you go up, the numbers are positive. If you go down, the numbers are negative. And you'll sometimes see these referred to as quadrants. So in this quadrant, formed by the x and y axis, both values are positive. In this quadrant, you can see we have negative x and positive y, so we'll have negative x and positive y values. In this quadrant, you can see we have negative x, negative y, that's quadrant 3. And this quadrant, we're going to have positive x and negative y. This is important when you get into the robotics part of the course, when you're moving the turtle around for different purposes. But it's good to get this nomenclature correct and understand how the numbers work on the XY coordinate plane. So there's some examples of coordinate pairs, and as I mentioned before, the x value is written first and the y value second. And so you can define any point by this pair. And one old school trick to remember how to write these is that if you're moving around, you're going to walk along the floor first and then go up or down in the elevator. So your X value comes first and then your Y value. To make that super confusing when we start working with the slope of a line, it's Y over X, change in Y over the change in X. But just to write the coordinate pair, it's the X value first and the Y value second. Okay, this is also a source of confusion. How do we draw angles on the XY coordinate plane? Well, our default value is 0, and that's if, in our case, with a turtle pointing this direction, it's 0. And then you can either go counterclockwise or clockwise. And this is equivalent to going left or right. But it's also, it's affected by how you write the values. So going counterclockwise, your values are going to be positive. Going clockwise, your values are going to be negative. So if you see a turn angle of 90 degrees, that's going this way. And then 180, and then 270, and values up to 360. Going negative, then you're going to be going this way. So if you turn minus 90, you'll end up down here, and so forth. Also, sometimes we refer to these as compass points. So this is east and north and west and south. And just for reference, if you have a circular protractor, that's how it's numbered. You can see there's 0 here. And they don't put a sign in front of it, but again, you can see that would be negative 90 here and positive 90 there. One other point is that lines on the XY coordinate plane are really vectors. A vector has got a magnitude, that's a size, and a direction, so it's pointing a certain way. And if we draw a line between, for example, this coordinate, which is 0, 0, and this coordinate, which is 30, 40, that is a vector. You can see it's got direction. And we can also, if we've got the turtle already pointed, so it's got a direction, we can just give it a distance and it will just draw. We just have to give it the length. So if you keep this vector thinking in mind, then the turtle makes a lot of sense. And it also builds the foundation for advanced mathematics. Vectors are used in all kinds of XY data. So you might have wind speed and direction, for example. Those are two different parameters. And you'll form a vector with the two of those pieces of information. So what are we learning from drawing? Well, we're learning how to write a logical sequence of commands. I remember when I was a teacher, teaching sequence in storytelling or in mathematics or anything else, it was kind of a key to self-control. You do this thing and then this thing and this thing, and you get this outcome. If you're just chasing your tail all over the place, you never get anything done. So sequence is a great way to learn how to control your behavior as well. Anyway, if you learn how to execute a simple sequence of commands, then you're ready to start working with control structures, and in our case we're working with for loops. You're also ready to work with containers. Lists are ordered, and order is key to how to use lists. And also you're ready to learn how to use conditions, if else, and if else. That's all very sequential. You're also learning how to be precise. You're learning about coordinates, and your distances and angles are measured precisely. And that's key to any kind of engineering, design, or robotics. You swing a robot arm half a degree off on an assembly line, and you're going to have to throw out your production line. And of course, we're learning coordinate plane geometry. And the marvelous thing about this map, you saw all those ordered pairs, is now you can reproduce what you're making. The computer records all that information. And again, this is key to anything that's automated. Once you have a map, you can do it over and over again. So that's true on an assembly line. It's true if you're 3D printing. Any process that relies on spatial data is going to use this map. We start by working with just 2 dimensions. That's our coordinate plane. And then we move on to 3 dimensions. So that's like your 3D printing. And 4 dimensions is going to include time as a variable, and it goes from there. You can get all kinds of multi-dimensional analysis. It gets really quite fun and uses some advanced mathematics. So the course itself, well, in Unit 1, we're focusing on understanding geometry, patterns, and basic controls. So we're going to draw geometric patterns with a robotic turtle. So always think of this turtle as a little robot. It's cute and everything, but it's not a toy. It's actually a robot. We're also learning how to write commands in Python, and we're going to do that to control points, lines, angles, arcs, and polygons. We are creating some pretty intricate designs by using for loops to repeat a set of commands. And some of the focus is on these rotated designs, but you'll see designs for staircases and a set of pan flutes and corrugated roofing. So that's getting into some very concrete applications. And it also goes over exporting your designs as STL files for 3D printing, SVG files for laser cutting, and PNG files are also used for laser, vinyl, and paper cutting for stencils and just for display as artwork. Unit 2 is really where they're learning how to build programs. So they're working with variables and functions and indices. They're organizing their code that makes it powerful and less prone to errors and easier to edit. So they're really controlling the program to create all kinds of designs. And again, this is the fun part. You get to make pretties out of this. And at the end, they explore rotational geometry, and we did that with the flower pots. And then Unit 3, it really digs into robotics. So when you have those skills that are learned in Unit 1 and Unit 2, now you're going to start working with sensor information, and these mimic real life problems. LiDAR is used it's used for navigation in autonomous vehicles. It's used to map topography. When you have a drone flying over an area and you're doing micro topography, you're using LiDAR. And you're writing algorithms to follow lines on the ground. This is what robots do in factories. Navigate mazes, search for objects. These are all robotic tasks. And this is really where we dig into complex conditions and really understanding how Booleans work as values and variables and expressions. And also we're using Python lists. So this is applied drawing, but not as artwork anymore. This is as robotics. Okay, so today we're focusing on Unit 1. And in sections 1 and 2, we're just going over the basics. How do you draw points, lines, and turn angles? In section 2, we get into a few extra commands that help customize your drawing, and you also learn how to extrude 2D drawings to 3D and export STL files for 3D printing. And there's an example of a 2-dimensional object, and we gave it a little bit of height with the extrude command. And you could export this very simple star and print it out on a 3D printer if you so choose. All right, so creating the turtle and drawing a line and displaying the line. Now, what I'm doing here in this webinar is giving you some background information as a teacher, so that when people get confused about something, you have a handy reference on how to explain certain things. So our first command line, and basically what you're doing is you're creating an instance of a class of turtles called NCLab turtle. And the default name we use in the course is Tina, but really it could be any name. You'll see some later on when you're doing local variables. We might use a T instead of the name Tina to distinguish it. You can name it after yourself. You can use a proper name. You can use V123. The rules are you cannot start the name with a numeral because Python will think you're doing something else. And also you're not going to make a name that's all caps because that indicates a keyword which runs a program. So we don't want to use all caps, and we don't want to start a name with a numeral. Those are rules. The other feature of this initial command is, you see those parentheses here? If you want to start your turtle somewhere else other than the origin, you can give it coordinates. So if I say BART equals NCLab turtle 3030, it'll start my turtle at x equals 30, y equals 30. So that's all about that first line, and I'll tell you 9 times out of 10 when a program doesn't work, it's because somebody forgot to put those parentheses. The basic way to move a turtle forward is tina.go. Oops, not there yet. And then you give it the distance, and keep in mind that each of these squares is 10. So if you want to move it 2 squares, you write 20. And then we always want to show our drawing. So tina.show will display the turtle. And we're using a syntax that is part of object-oriented programming, or OOP. And you're writing your object, Tina, and then it always has a period, and then the command, and then any arguments that belong to that command. So we're telling it to go, we're giving it the distance as an argument. Now I made these little videos, and I know that I still haven't figured out Zoom on how to transfer the audio. So I'm just going to show you that they exist. I created 4 new videos that explain what's on these slides, and you'll have links to all of them. So the second video that I've made has to do with angles, and it has a little program that runs through these procedures. You start off by turning left and right. And of course, in Carol, as you probably remember, that Carol only turns 90 degrees left or right. You can't give it the degrees. Whereas the turtle, you can specify degrees. You can even specify them as a decimal. So for example, you could say 20.5 degrees. You can get quite precise on your turn angle. Again, this is going back to the XY coordinate plane. The left turn is equivalent to a counterclockwise turn with positive value. And if you're typing quickly, you can abbreviate it as LT. And right is a clockwise turn, and you can abbreviate that as RT. When you get into the angle command, this really respects the naming conventions of the XY coordinate plane. If you write Tina angle, it is always drawn from Tina, or the turtle, facing east on the axis, or a line parallel to the axis. So let me demonstrate that. I'm going to go out of here, and I'm going to go into the desktop and open Creative Suite. And so the turtle's under programming. You go to programming, you go to Python turtle, and I'm just going to erase the sample code. Okay, so I'm going to start by creating a turtle. Let's stick with Tina for now. NCLab turtle. And did you see how, let me see if I can make that a little bigger. Okay. That should be easier to see. You see how it changes color? That means I spelled it correctly and it exists. So that's a key right there that you entered it correctly. And then I'm going to use the angle command. Angle, and let's turn it 30 degrees. And then I always want to display my results. So I'm going to do that. And now I've made it so big I can't get down to the run. Let me make it smaller again. Okay, I'm going to run my program. Okay, and I'm going to set the view to 2 dimensions. Okay, can you see how the turtle's turned? So if it was 0, if I put 0, which I wouldn't because that's default, so that would be a waste of a line. There it is facing east. I put 30 in, let's try 100. And now you can see the turtle is, this is 90 plus another 10 degrees, so the turtle is facing that direction. So if I drew a line, Tina.go, and let's just give it, oh, I know, 60, that's 6 squares worth. Off she goes. So that's just a basic script, of course, but I did want to make sure that you understood that angle acts exactly like that protractor and the main conventions. Okay, where were we? We're here, and we're going to go back to present. So that's a little bit about turning angles. We can also change how our line looks, and we can change the width, and we can change the color, and there are default values on those. And this calls from a color library. And we can also write RGB codes. So let me show you that on the app as well. And this is all in those little videos that I posted. Okay, so if the default width is 1, but let's just keep her going at that angle, doesn't matter. Let's go Tina.width, and let's say 5. Okay, so if I draw it now, boom, I got a nice big fat line. Okay, now if I go outside the window for the parameters, I'm just going to get an error message. So if I set it at 15, for example, it'll come back and say line width must be between 0.1 and 10. So that's something to keep in mind. I'm going to put it back to 3, and then I'm going to give it a color. So you notice that the default color is blue. It'll draw in blue if you don't tell it anything otherwise. If I make it green, whoops, see, they didn't like that. When I did the M, it didn't change color. When I go and spell it properly, it changes colors, and that lets me know that this is a valid keyword. So I'm going to run that. So there's my thick green line, and then I can do something called lists, and I'm going to zoom in again for this. Let's see, control, so you can see it. And lists are always enclosed in square brackets, and a color list, RGB, stands for red, green, blue, is always composed of 3 values. So if I go 0, 0, 0, and then I have to close my bracket and run the program, and I'll go reset here to do that and run it. If you guess black, you're correct. The zeros are all black. And the values range up to 255. So if I replace all those with 255, then I get the opposite, which is, of course, white. If I just put in 255 for the first value, it's RGB code. So my first value is red, and I'm going to get a nice bright red line. If I put it in for the second, I'm going to get green, and if I put it in for the third, I'm going to get blue. And if I start combining them, I get the secondary colors. So this is RG, and this is not intuitive if you're used to a color wheel, but this is halfway between red and green. And what we're going to get is this. we're going to get yellow. And if I switch those, so I'm going to put a 0 here and a 255 at the end. So now I'm halfway between red and blue. And I get magenta. And then the third intermediate, if I put 255 here, I'll get cyan. So that starts to sound familiar. Yellow, magenta, cyan. Those are the colors of your printer inks, and they're combined with black sometimes as well. So really you can start playing with this. And I gotta tell you, kids just love playing with RGB values. So I'm just gonna mess around here. I'm gonna put in 160 there and a 30 there, and let's go to, I don't know, maybe let's go 180 there. Okay, so it's R, and it says it should be a purplish color because I suppressed the green. There it is. Yeah, it is purple color. So this is something that, you know, even young children can have an awful lot of fun writing very simple code based on these basic ideas. All right, back to the slideshow. Okay, so that video basically goes through what I just demonstrated. And then there's different ways to move your turtle around. We already used the go command to draw a line, but I grouped these 5 sets of commands here to show you different ways to draw lines and how to lift the pen and put it back down, and how to use the back command and how to use the home command. So let's try those out. Okay, so I'm going to blow this up again. You see what I'm doing. All right, so let's say I'm now at I've got to that position, but now I don't know how to turn the angle or draw the line, but I do know I want to end up at this point. And if we count on that, that's going to be negative x, so that's 10, 20, 30, 40, 50, 60, negative 60, and it's plus 10 on the y-axis. I can say, Tina, go to, and give it those coordinates. So I said minus 60 and plus 10, and then let's see what she does. Oh, there she is. And so that's a really nice little command to use. It sends you exactly to the point you need to go to. It's really good for drawing shapes like triangles, which are hard to figure out angles and stuff for, but you know where the endpoints are. Remember that the school standard talked about drawing polygons based on coordinate pairs. So this is one way you can do that. It's what we say computationally expensive, even though it's easy for us to do this. The computer has to work fairly hard to get us there. So you use it when you need it. Another command, let's say I want to move the turtle, and I'm going to just turn her a few degrees. We're going to go left, and I'm just going to say about 30. But then I want to pick up the pen because the next line, I don't want to draw it, I want a space. So then I'm going to do Tina, pen up. I'm going to write it out, but you can also write PU, pen up. And I am going to do Tina, go to, and I'm just going to come up with a number. So let's say plus 10 and minus 50. Minus 50. All right, and then I'm going to put my pen down again. And the words come from old-fashioned pen plotters, where they literally did lift the pen, and they moved the pen around on the plotter and put it back down again to start drawing again. So that's where the wording comes from. And pen down can be abbreviated as PD. And then I'm going to draw a line. So we'll go Tina, go, let's say, I don't know, 30. All right, let's see what happens. 30 must be my favorite number today. I used it 3 times. Oh, there it is. So there's the line I drew. And now Tina's drawing way down here. And I'm going to step through that code so you can see all the movements. So there's the turtle. And now we've set the color. You can see the turtle change color. And now we've set the angle. And then we went 60, a line length of 60. And then we told the turtle to go to this spot. So you can see all this stuff is built into that one command. And then we picked up the pen. And then we aim the, oh, yeah, sorry, we turned 30 degrees. So that's the turn. We picked up the pen. And then we go to this coordinate. And that's where you see the jump. Now, Tina's still aimed in that direction. So when I put the pen down and I draw the next line, it's drawing a straight line in that direction. Okay, oh yeah, and then let's say at the end, I just want to go home. Home is a nice reset. It'll set the turtle in the default position at the default direction. I'm just going to run it this time. And there's our turtle back at the beginning. All right, so, oh, I didn't go over back. Well, back acts like pen up, pen down, but it just backs the turtle up along a line. Sure, let's just show that as well. Okay, so where we went 30 here, I'm going to insert a back command. Tina, back, and we'll go halfway on that line, so say 15. Oops, 15. And I'm going to change the color. Let's make it black. How about orange? Orange. There we go. And then I'm going to turn it 90 degrees. Let's go 90 left. And we'll draw another line. All right, let's run that. Okay, so, and I'm going to zoom in. I'm going to see if I can zoom in so you can see this a little bit better. I don't think it will let me move this. Let's see. Oh, yes. There we go. Okay, so you can see I backed up on that line and I changed the color first. If I didn't have pen up built into the back command, this would now be orange. So back is one of those nice commands like go to that does a whole bunch of things for you without having to write extra lines. And then I turned it left and drew a short line. And so that's the end result. Again, all that information is built into that little video. And you can share those with your users. All right, so we're still primarily working on the XY coordinate plane, but we are going to use the Z-axis a little bit, and that is to create these 3D printable objects mostly. And you can do that a couple of ways. You can vary the height with a height command. That's really covered in section 3. Or you can extrude the whole drawing with the extrude command, and that's actually introduced at the end of section 1. And then what we did with the flower pot workshop is we rotated the line around the y-axis with these commands, but that's learned in unit 2. We're not covering that today. Any 3D object, once you've made it 3D, you can export it to a 3D printer by creating an STL file from the viewer menu. And here's some examples. So if you want to tie a project into Unit 1, you could use some of the information in Webinar 5 that was creating these medallions. And the one that created the rotational objects, that's Webinar 11, that's the flower pot. So I just put those links in here for reference. Okay, so it's section 4, not section 3. The height command is going to set the drawing height ahead of the line. So let's go back to our program here. Well, here we have a little program that I've written to demonstrate height versus extrude, and it creates this design here, which you can see these are 5-sided regular polygons, and there's 1, 2, 3, 4, 5, 6 of them. And by the end of unit 1, people know how to create these. These are nested loops that are used to produce this design. In this case, I have height activated, and extrude, you'll notice I put a little pound sign in front of the command, and that it's grayed out, and that means it's inactive. I've commented it out. So we're going to use height, and if I run the program, I should get what you see in the viewer. And there it is. Now, height, like width and color, are written ahead of the code that you want it to work on. And they're useful in that you can change that. So if I wanted to make another design afterward and I wanted to have it a lower height or something, I can rewrite that height command down here, and let's just put it in there for fun. So tina.height, let's make it 1, and then I'm going to run the same thing again and do something a little different. And I'm going to make it range 4 and make it 10 in length, and we'll turn it 90 degrees, and let's make that oh, let's just leave it as that. Okay, so if I run it, all right, now if you look at it, turn it sideways, you'll see that little figure in the middle is a lower height. So that's the advantage of the height command, in that you can change it throughout the program. I can just take that out again. If you're going to make something the same height for the whole object, you can just use the extrude command. So I'm going to comment that out, and I'm going to make tina.extrude live, and I've used the same value for the height, so it should come out as it did before. And there it is. So that's just a simple command that you put at the end of the program. It hides the turtle and it extrudes it, and then you can export it as an STL file if you want to print it. Okay, this is a little bit about exporting. And one of the things you can do, a very simple project if you have a color printer, is you can just export a PNG image and create a little gallery walk. This time let's practice exporting an image file. So this is very similar to the design we did before. I added a little spice to it. I put the color command inside the loop, and I'm using a command called rancolor, and rancolor will pick a color at random. So for each of these pentagons, the color will be randomly selected to a different color. All right, so let's run this. And I like those colors, so I'm going to stay with that design. And let's say I want to export a picture of this. Well, I can turn off my axes and my grid, and then I just have an image. I can still manipulate it if I want. I can zoom in and out. And once I have an image I like, I can export it as a PNG file. So there's a PNG file, and if we open that up, that's what it's going to look like. So just the image, it's just a snapshot. A couple of other little tricks here. So if you're sending an image to a cutter, you want to have it in 2D, and you can either change that on the viewer, just change it to 2D there, or if you're going to run it, then use the Tina hide command and take out the extrude, and it'll automatically display in 2 dimensions. like that. So you can see I can't rotate that anymore, but it's a very clean image, and you're going to have you're not going to have those fuzzy intersections. They'll be nicely defined. So that's a little bit about exporting image files. And image files are used to cut stencils and on laser printers as well. All they need is 2 dimensions because they supply the 3rd dimension. All right. So I went into a lot of depth on sections 1 and 2 because really they're the foundations for everything else. If you're comfortable with drawing lines and turning angles and manipulating the line and making files out of it, then the rest falls into place. In section 3, we're starting to get into for loops, and these are what we call indexed for loops. And you start by drawing simple polygons. And then there's an example of using the height command differently. This makes a little crown. So section 4, it's also using for loops, but the patterns are a little more complex. And you learn how to draw curves using arcs. So basics on for loops. Remember Carol just did repeat for and then go left? Well, this is the equivalent in Turtle. You're creating your turtle, and then you're using what's called an indexed loop. So this index is the letter I, and we're going to repeat it 4 times. And so we'll go 30 and turn left, and go 30 and turn left, and go 30 and turn left, and go 30 and turn left. And then once the indent stops, that's all the commands that are going to run in that loop. And once it's run it through it 4 times, then it'll jump out and do the next line, which is the show command. So syntax. Once you get started to understand indexing a little bit better, it's actually I equals 0, I equals 1, I equals 2, I equals 3. And that's covered in Unit 2. Always make sure that you end your for loop statement with a colon, and it'll actually automatically indent for you. The convention for indenting is 4 spaces, and anything that's indented is what's going to be repeated. The neat thing about studying regular polygons is they're really all variations on a circle. Remember, a circle is 360 degrees, and there's a relationship between the number of sides and the angle of turn. So if you take 360 and divide it by the number of sides, then you'll get the angle of turn. And by the time you get to 60 sides, it's pretty smooth. You can barely, if you zoom in on that shape that you produce, you can just see that 6-degree turn, and it's drawing a pretty smooth circle. In section 4, we're also using index for loops, but this time it's not just a turn in a circle. In this case, we're making a staircase, and all of these are demonstrated at the beginning of the sections. Drawing arcs, really this gets back to angles, and you're looking at 3 things. How much you're going to turn, that's the degrees of turn, and you can see this little turtle has turned 180 degrees. And then the radius of turn will tell you how big it is. So in this case, you can see the radius is 10, and then it's drawing to the right, and you'll note that these are written in quotation marks. And this is demonstrated on level 4.4. And then finally in section 5, we're drawing nested loops. So these are loops within loops, or repeated patterns within repeated patterns. And again, you're making something that's pretty, it's rotated. And the way that works is as follows. So here's the code that just drew that previous object. I'll go back to it for a moment so you can see it again. That's what we're drawing. And you can see there's 2 for loops. There's one with an index that's named I, and one that's an index that is named J. And you see this first indent here? Well, those are the commands that are going to be run by the outer loop, the I loop. And then the second indent, these are the commands that are going to be run by the inner loop or the J loop. So the I loop starts, and its first task is to run the J loop, which will create a hexagon. It's going left, going left, going left, going left 6 times, makes a nice little hexagon. And then the second task for the I loop is to turn the turtle left, and then it's going to do the whole thing all over again, and that's going to make this pattern. So you've got a hexagon, and then it turns, and another hexagon, and it turns, and another hexagon, and it turns, and another hexagon, and it turns, and another one, and finally you have 6 hexagons to make the mosaic pattern. Things to watch out for in for loops: make sure you get that colon at the end of the command line. And make sure you understand which commands are being run by which loop. So these indents are run by this loop. These indents are run by this loop. Okay, so some things that are inspiring, and if you ever really want to get crazy, you can have them make a simple pot holder. Knit and purl is a repeated pattern. Knit, purl, knit, purl, knit, purl, knit, purl. And then when you go to the next row, that's your outer loop. That's a nested loop. And of course, this pattern here is a little fancier, but have them look up different knitting and weaving patterns or primitive art. Wonderful examples of nested loops. And another source of inspiration is music. This is, of course, a heartbeat, but most popular music is based on heartbeats. They're repeated patterns, and that's why they feel so comfortable to people. But these are real-world examples of nested loops. If you're going to do a workshop, I'd allow 1 to 2 hours per section, and there's 5 sections. If they're just running through the course, they'll complete it in about 6 hours of computer time. And then if you include some offline activities, I would allow about 10 hours total time. So for example, you could do a weekend workshop, or run it over, depending on your coding sessions, that might be 10 coding sessions. I would have them just start the course. A lot of these instructions that I've gone over with you, they're built right into the course, and there's instructional videos that help, and it really does build from simple to complex. The materials from this deep dive I would use as a teacher to troubleshoot understandings, especially about the coordinate plane. That's usually where people get hung up. Once they understand it, the rest is pretty easy. I would set up a drawing station, some art boxes just with pencils and rulers and compasses and protractors, square paper, and that'll give them some offline practice with the coordinate plane. And then 2 games, Battleships and Destination. And these can be played paper and pencil. When I was a kid, my dad and I played Battleships all the time with squared paper. And in some ways, I prefer it to the fancy plastic expensive ones with lights and whistles and everything else. When you do it pencil and paper, you're really building some additional skills. And you can start off very simple, and then you can start getting fancy, start specifying quadrants, or maybe using quadrants as a clue to where the battleship is. And that's going to build a lot of understanding. Destination, basically, you're going to have your users create a set of instructions, and the other person has to draw out according to the instructions and see if they get to the point that they're supposed to get to. And I'll include some little worksheets with this webinar so that you can just have those instructions out and they can play games. So drawing station, I repeated myself here. Battleships and Destination is games. And then you can print out those images like I showed you, PNG files. You can make a nice little walk through gallery. They can also share their code with URLs the way we've been sharing in all the other courses. And they can create games like we've done in the other courses where they print some explanation of their drawing. And then of course you can print things out on a 3D printer or create stencils. This project here, this is a nice end of unit project, and it's printing your initial. So by the end of this unit, they'll know how to use the arc command. The arc command can be used to draw a little circle for a pendant holder. So if they create their initial and then extrude it, this is a printable object, and it's personalized and it's simple. So that's a very nice little project you can do at the end. And of course, you can also do the pendants from Webinar 5. Both of those fit very nicely with Unit 1. If you're going to group sections, sections 1 and 2 go well together. Those are all the basic commands. And sections 3 and 4 really work through repeated patterns. Section 5, because it's nested loops, needs a bit of focus. You could probably run that on by itself. So you could, if you want to alternate with offline activities and artifact creation, you could work on the course, then do some offline drawing, play those kind of games. Go to the app and create and save drawings and share those as URLs or as PNGs for the gallery walk. And then get inspired. You know, watch videos on robotics, see if you can detect the type of movements we see in the turtle. Do searches on mosaic art, on primitive art, on font creation. If they're making that initial medallion, they might be very interested to see how people vary angles and thicknesses to create fonts. And well, we've come to the end. So what did we do today? We discussed how the turtle was developed and a little bit about why we're learning Python. Went into some depth on understanding the XY coordinate plane, and we went through the first 5 sections of the course. I ran through sections 3 through 5 a little quickly, but there's great demonstrations at the beginning of each one, and they do a good job of explaining how these for loops work. We learned how to practice the concepts in Unit 1 and some ideas for creating projects based on Unit 1, and how you can tie these concepts to math and art and design and robotics. And of course, robotics is really taught in the last unit of this course, but if they go searching around for videos on robotics, that might inspire them a little bit in pursuing this to the end. All of these materials will be on the community page, just like the other webinars. If you ever have any issues, you can contact NCLab through support, and the button on the desktop is working properly now. It'll automatically contact support, even if they don't have an email address. You can call this number for phone support. And don't forget there's materials related to the course at instructor-resources on the website. During the live recording of this webinar, we had a question about a list of commands. The commands are in the Turtle textbook, but we will include a simple list with the webinar materials that makes it easy for users to create their projects. Our next webinar is going to be on data. We're going to draw from the Python courses and Carol. That will be at the beginning of June, and it'll be the last in this series for this year. Look forward to seeing you then.